Thank you very much, Professor Park. That was a really interesting talk on sensing, and I think that we'll have lots of questions to come back to that in the panel discussion. So the second speaker we have in this session is Professor Guoying Gu, who leads the Soft Robotics and Biodesign Lab at Shanghai Jiangtong University. So Professor Gu has made significant progress towards bio-inspired hands and skins and sensors. He's going to be talking today about his work on prosthetic hands, sensing skins, and modeling and control. So Professor Gu, thank you very much for joining us. I can hand over to you and ask you to start your talk, please.
Yeah, thank you. Can you see my?
Yeah, that's perfect. We can see and hear you very clearly.
Okay, thank you, Joyce, for the introduction, and also thank you, Professor Ida, for the invitation. So today, I will give a talk on our recent development on design of control soft robots, mainly focused on the pneumatic actuation and also some recent work on modeling and control of self-control soft robots. I'm Guoying Gu from Shanghai Jiangtong University. This slide, I also just see the interest of our group. We focus on to use the new soft actuator and sensors and to develop different bio-inspired robotic mechanism, and then try to develop different soft robotics applications, mainly on the manipulator and locomotion on the wearable robots, and also focus on some nonlinear modeling and control. Today, I would like to just focus on pneumatic actuator soft robot for design and control. So in this talk, I maybe mainly focus on our first work on a software prosthetic hand, and next on the modeling and control of the software continuum manipulator. Yeah, as we know, the prosthetic hand has developed for more than 100 and since the 18th century. But we can see until now, all the prosthetic hand are mainly built with the rigid structure and motor. It is different from our human hand without lack of complaints, and the mechanical structure is very complex. Therefore, we wanted to develop a new soft and lightweight prosthetic hand. On the other hand, recently, the researchers started to embed the sensors for the prosthetic hand. So based on this work, we developed a new class of wearable software robotic hand for amputees. On the first slide, we will to develop a new wearable robotic hand, and at the it should be compliant, lightweight, and low cost. On the other hand, we should to intuitively controlled by the human. In this work, we use the SEMG signals by the user, and then when we touch the object, he can give a real-time feedback to the human. Yeah, in this work, we use the electrotactile stimulation. So this is the diagram. Our work with the simultaneous electrical control and tactile feedback. Firstly, he can to use the SEMG sensor to understand the intent of the amputees. Then use the myel control. He can to control our soft hand with the fingertip. They have some touch sensor, so he can to measure the touch force. Then with the electro stimulator, he can to use the electrotactile for the human to restore his tactile feedback. So for first, as a first step, we use the fiber reinforced elastomer tubular structure to develop a softer finger to mimic the soft and joint and rigid bone anatomy with the 3 rigid segments inside the softer tube. Then we can to design the length of the flexible joint to mimic with the only one pneumatic actuation. He can do this to develop the multi joint flexion. Then we can to build a bionic hand like this. We can use the simulation and experiment to show that every hand has the flexion movement, and on the stem he have also another abundant with the pedal actuator. Then we verified our dexterity with a standard grasp test. Finally, we embedded all the components in the prosthetic hand, and we developed two modes. First, a lightweight mode to put all the components in the bag behind the subjects, and we can also to develop and test one to put all the components into the prosthetics. And in this slide, we can see when we use this new soft hand, the transradial amplitude can very easy to use it to handle some fragile object, and can also to the interaction with the other peoples. It can to use in the nearly daily activities. And this work also highlighted by nature so we developed a tough prosthetic hand to obey the muscles commands. On the other hand, we developed the ionic hydrogel elastomer hybrid structure to build a captive sensor. And our sensor, with this sensor, we can to establish the relationship of the fingertip force with the stimulated electrodes to help the amplitude to understand which fingers can be touched. For example, in the video, we can see when we touch the finger of the soft hand, the subject cannot see. He can to see which finger is pressed or which multiple finger is pressed. And finally, we also use to combine the myoelectric control and the tactile feedback to help the subject to know which objects is handled when he can feel the force. Then he can to lift his hand. Manipulators. As we know, for the rigid robots, we have very good models to describe the mechanism, kinematics, and dynamics, because in all the motion is generated in a separate joint variables. We can to use a mathematical model to describe them. But for the soft robots, the kinematics is based on the string field and discrete field. He can either very easy to develop a relationship between them, and the force is distributed. Therefore, currently there is no standard modeling and framework for this kind of robot to analysis and control. We can also see to address this challenge, the researchers have developed several works, for example, with the PCC method and the Euler spiral method and some model function method. But all these method, because he used a low model dimension and high efficiency, but it neglected the 3D deformation of the material and structure. Currently, the finite element method and lambda system modeling provide a new framework to do this to further versatility. But the model generally have a high model dimension and a low efficiency for real-time control. In our work, we use the absolute nodal coordinate formulation method. We can, on one side, to full discretion the discipline field and the string field, and on the other hand, we can to obtain the high accuracy and very good computation efficiency. This is the model of this kind of the formulation. When we use it to describe the kinematics of the soft robots, we found it can very easy to develop user configuration parameters and to use the differential field, and then we can to establish the relationship between the input pressure and other final task variables. Therefore, we can to derive the kinematics algorithm. It can also consider the external force. Then we can to user formulation, equilibrium equation, and also to define the general rules based on the integration algorithm. We can see when we use it to very easy to control the series continue arm and also the parallels of the robot arm, focus on some to use the software actuator and sensors, and also to develop some 3D printing method, and finally to develop some software machine and robots to verify our method and work. I also thank the lab members and also the support from our university and the government. Thank you.